Exponent rules part 2. When you have a power to a power, the exponent 3 here is telling you that you will multiply x to the 5th 3 times. Then each of these x to the 5ths is x multiplied 5 times. When you say power to a power, you're really saying I have 3 sets of 5 x's that are multiplying. So that helps you to see that power to a power is a situation where you multiply the exponents. People often get this confused with the time when you multiply. And let me emphasize, because when you multiply, you have a situation of, say, x to the 5th times x cubed. That's when you add the exponents. So make sure you understand the difference between here, where the base x is written 2 times, and I am multiplying, but over here, the base x is written only once, and it's a power to a power. And there is the exponent rule that you need to have for power to a power. The next exponent rule is the issue with fractional exponents. According to the power rule that we just learned, if I have x to the 5th power, and I put that to the power of the fraction 1/5, that means I multiply 5 times 1/5. What is 5 times 1/5? It is 1. What is exponent 1? Not needed to be there. So we have just plain old x. Now I want to talk about the fact that a 5th power is the inverse operation of a 5th root. They undo each other. And what did we learn about when functions undo each other? We learned that we come out exactly as we originally went into the first of the 2 inverse functions. We end up with x. So this is a little bit of a way to show you that when you have a fractional exponent, that is actually referring to a root with that index number. If you combine having an exponent with having a root, then you end up with the numerator of that exponent is the power. And like a tree, roots are at the bottom, roots are in the denominator. The next rule I'm going to go over is the distributive property of exponent or root over multiplication. I'm showing you with an example. Let's say we have x times y in a parentheses, and that is put to the power of 3. That means that x times y is multiplied 3 times. Now, order of multiplication doesn't matter. So we can choose to group together the 3 x's that are multiplying, and we can choose to group together the 3 y's that are multiplying. And then we can see that ultimately what we have is x cubed times y cubed. And that is the distributive property of exponent over multiplication. Anytime your outside operation is a repeated operation of the inside operation, what you have is a distributive property. Then I'm going to show you the example with roots. I'm actually using numbers. If I have the cube root of 8 times 27, the 8 times 27 is understood to be in a parentheses under that cube root. Well, what is 8 times 27? You can use a calculator if you like. It is 216. You can also use a calculator to figure out what number multiplies 3 times to get 216, and 6 is that number. In the second line, I have the 2 cube roots separated with multiplication being outside. So it's no longer in a parentheses. It is now separate. What is the cube root of 8? Well, 8 is 2 cubed, so the cube root of 8 is 2. 27 is 3 cubed, so what is the cube root of 27? It is 3. And we end up getting 2 times 3 is 6. Just like what we got if we were to first multiply the 8 and the 27 and then take the cube root, or cube root each individual 8 and 27 and then multiply that result. So 2 different examples to show you the distributive property where you have an exponent or a root over multiplication. I have an exponent over division. The exponent 3 just means I'm multiplying the x divided by y 3 times. And that is exactly the same thing as multiply the things across the numerator to get 3x's multiplying, and multiply what is across the denominator to get 3y's that are multiplying in the denominator. So you can see that either you do division and then you cube, or you can individually cube and then do division, and that is the distributive property of exponent over division. Distributive property of root over division, I have an example right here. 64 divided by 8 is 8. The cube root of 8 is 2. I could also distribute that cube root over the division so that I first cube root each individual number. The cube root of 64 ends up being 4. The cube root of 8 ends up being 2. So I do the individual cube roots, and then I do the division, and I end up in the same place. This is the distribution property of either an exponent or a root over the property of division. I have a few examples to show you, and then you'll do some homework problems and see how it's going. What I'm doing with this example is I am first taking the number that is inside the root, and I am writing it as the smallest base that I can use to a power. 81 is a repetitive multiplication of 3, 27 is a repetitive multiplication of 3, and 32 is a repetitive multiplication of 2. You can now rewrite it in the fractional exponent form. And this is the part that people aren't going to be very fond of, but be glad you have a calculator. Now we add the exponents that are from the same base and multiplying. So I have 3 to the power of 4/3 plus 3/2. This third expression has a different base than the 3's, so I cannot combine them. Add fractions, I need to get a common denominator. And then I am able to add the numerators and keep the denominator. The power of 6 and a 5th root means that x is to the power of 6 over 5. X cubed in a 5th root means x to the power of 3 divided by 5. When I am multiplying and I have the same base, I am allowed to add the exponents, add the numerators, keep the denominator, and that is a way to rewrite the expression in fractional exponent form. 2 of these 3 expressions that are multiplying use the y variable. The other one uses x, so that x is going to end up being a loner. We rewrite the 6th root of y to the 5th as y to the fractional exponent 5 divided by 6. We rewrite the cube root of x squared as x to the fractional exponent of 2 divided by 3. We rewrite the cube root of y as y to the fractional exponent 1/3. The like base exponential expressions are allowed to come together, and I add the exponents. Again, x to the 2/3 is a loner, and it's done. It's in its fractional exponent form. For the y, I have to get a common denominator, and then I can add the numerators and keep the denominator.